And action. Hello, everybody. We're getting started. Woohoo! Everything's great. So let's go to chapter 18. If this would start sharing at some point, that would be awesome. Okay. Does it look super blue for anyone else? No? Okay. I think I fixed it. I updated WebEx on my laptop and now it looks completely different. So we're trying to keep it together. So, chapter 18. Last week we talked about this first stuff, tautomerization, racemization, etc. And yesterday we talked a little bit about acidity, and then we got into some reactions. So we talked about the Hels-Volhard-Zielinski reaction last. And just to review, we said that if there is Br2 and PBr3, PBr3 just turns OH into bromine, and the Br2 is going to turn an alpha hydrogen into a bromine. So for this reaction, we get bam, bam, bam. We turn the OH into a Br, and we add a bromine here. And for the second example, nothing is changing in the first two steps, but we're adding an extra step where this H2O is going to do a nucleophilic substitution reaction, and it's going to turn this back into an OH. So the answer to this reaction would be, bam, we add this blue Br, and we're actually going to end up with an OH back on the carbonyl. So that's kind of where we ended up last time. Do we have any questions, comments, or concerns about that? Okay, so if there's no questions about that, we're going to go to the next reaction, which is an alkylation. So let me write that down. So the alkylation is going to be very similar to the ones we did before. So we have a carbonyl, bam, right? Except now we're going to use slightly different reagents. So if we go back up here to what you guys have on your worksheet, the general reagents for this reaction are going to be this guy. And we know from a couple chapters ago that this is an alkoxide. And we also need an alkyl halide. So I'm going to just go ahead and redraw that over here just so I give myself more space. So we had Na plus and this guy. And we also had, do it in blue just because, we had this. So our alkoxide has a negative charge, and we know that anything with a negative charge is a what or a what? A base or a nucleophile. Awesome. So in this case, we have 1, 2, 3, 4, 5 alpha hydrogens. So we know that the alpha hydrogens are acidic because they're in the allylic position. So this guy is going to act like a base. Which alpha hydrogen is it going to take? Alpha 1 or alpha 2?
Two.
Okay, yes, I agree. So we're gonna, bam, steal that hydrogen. And now that we have a negative charge here, what is this guy called? Enolate, sweet. So this is called the enolate. And this whole chapter is based on enolate chemistry, enolate reactions. So the enolate is going to act as a nucleophile. And the reagents we have left are, we made this alcohol, so we can write that on the bottom. And we have this alkoxide, right? So this nucleophile can go ahead and, almost like an SN2 mechanism, it can attack this carbon and kick off the leaving group. So we end up with always count your carbons. So 1, 2, 3. 1, 2, 3. I see students like miss a carbon or put an extra carbon all the time. So just make sure you're keeping track of those suckers. All right, so how do we feel about this so far? Good, bad, terrible? Good. Okay, cool. So do you guys think there are any other steps we can take here? Is there anything else we can do? Or are we done? I feel like everyone's like, I don't know. These are never done. They just go on forever. I think we're done. Yeah, it does seem like we're done. And for once, we actually are done. So all we're going to do is add one carbon chain onto the alkyl position. So how come in, I don't have it drawn, of course I don't, but how come when we have this same exact molecule reacting with Br2 and base, we get multiple bromines added? Versus the alkylation, we only get one carbon chain added. Does anyone have any ideas? And it's okay if you don't, or it's okay if you want to completely guess and try something out. But I do want to hear an idea from you guys. Everything's on fire anyway. You know. Different reagents, yes, that's true. So think about the different reagents. So like here we added a bromine. Is bromine electron donating or electron withdrawing? It is electron withdrawing. So is an electron withdrawing group going to make this position more acidic or less acidic? Okay, so someone said donating. So don't feel bad if you thought donating. Just remember, it is a if we think back to chapter 15, halogens are withdrawing groups, but they direct, orthopara. So don't get those two like kind of mixed up. Bromine is super electronegative, and it's going to just pull this electron density. Therefore, it is a withdrawing group. Whereas this guy is an R group. R groups are electron donating groups. So it's bringing electron density to that carbon. So in this case, we're actually adding halogen makes the alpha position more acidic. And when we say halogen, we can say any electron withdrawing group. Whereas adding electron donating group makes alpha position less acidic. So for that reason, in the alkylation reaction, we only add one time. However, in the halogenation, specifically with base, we can add twice. So does that sort of kind of make sense so far? Yes? Okay, cool. So let's go back up here. Oh, just kidding. We finished that page. Here it is. So let's do a problem. Does anyone have any idea what LDA is? I read the yes from earlier and I was like, okay, then tell me. Okay, it's fine if you don't. I don't believe Dr. West talked about it too much. Lithium something. Yes. Okay, cool. So lithium is going to be that spectator ion with a plus charge. And the rest of it is going to be this guy. So this is lithium diisopropyl amide. So a lot of words to say this is a base. If you want to be even more specific, this is a bulky base. So as far as this class goes, this is the only bulky base we're going to talk about. And it is important to note, so important that I'll write it on the side, bulky bases can only steal alpha hydrogen from the least substituted side. So for example, in this case, we have alpha 1 versus alpha 2. If we had NaOH or literally any other base, which alpha hydrogen would we take? Alpha 1, correct. But since we have a bulky base, we have to steal the least substituted side. So in this case, which alpha hydrogen are we going to take? Alpha 2, correct. So, great. Now that we got that out of the way, does anyone remember what an OTS group is? So this is something we talked about, but it was a while ago. I'll give you a moment to think on it. Okay, so it doesn't seem like you guys remember, and if not, I mean, if you do remember and you just don't want to say it, that's fine too. But basically, OTS stands for tosylate. And we know that tosylate is basically a protecting group, right? And it can also function as a leaving group. So in this example that we did just now, our leaving group was our chlorine. But we could theoretically have any leaving group here. For the purposes of this class, he's only really going to use halogens or tosylate. So when he says OTS, all you have to think to yourself is this whole thing is going to be a leaving group. So what you're going to add to your chain is actually C2H5. All right, now that we talked way too much, LDA is going to steal this hydrogen, right? And we end up with a negative charge. That negative charge is then going to attack our methyl chain, or excuse me, our alkyl chain. It's not a methyl. Once it attacks, it kicks off the leaving group in an SN2-like fashion, and we end up with the ugliest benzene ever, the ugliest cyclohexane ever. And attached to it, we have 2 carbons, so it shall go like this, 1, 2. Any questions on the mechanism itself? Okay, if there's no questions about the mechanism itself, and also feel free to ask while I continue talking, but we're going to look at the answer choices, and we're going to see how we could easily look at these answer choices and pick an answer. So first of all, if you look at these reagents and you can tell, hey, this is going to be an alkylation, you know that all that's going to change here is we add a carbon chain, right? That's all that's going to change. So this answer and this answer are both trash choices because we got rid of the carbonyl and we created an ether here. That's not an alkylation reaction, that's garbage. This one, and this one all added the alkyl chain. However, here we added alpha, here we added alpha, here we added beta. So this is trash. So if you're stuck between A and C, you already have a 50-50 shot, and I can respect getting confused here a little bit, right? Because you know the basics. You know it has to add a methyl, or keep saying methyl, an alkyl group to an alpha carbon. So what you really need to think about is it a bulky base or not? If it's a bulky base, we know that the less substituted side is the answer. If it's not a bulky base, the most substituted side would be the answer. Sorry, my stutter is just really killing me today. Let me know if I'm speaking too fast or if you get lost or anything. All right, so leave this up for a second and see if anyone has any questions, comments, concerns. Excuse me, oh my gosh, or anything of the sort. Today is a very sleepy day, if you guys couldn't tell. All right, so if we don't have any questions, we're going to go on to the next reaction. So these reactions are called acetoacetic ester synthesis reactions, which first of all, in and of itself, is a mouthful. Second, you have to know that this is not the final product. This is the starting material. So you are not making an acetoacetic ester. I don't know how or why they name these things the way they do, but that's just how it is. And before we actually go into the reaction, there's two reactions that are almost exactly the same, but they are slightly different. So we have the acetoacetic ester and the malonic ester, which again, the malonic ester is the starting material. So before I show you the reaction, we're gonna go over some naming stuff that tends to confuse people. I'm making a new page, so don't mind my weird scrolling. So this is the most general way that I can show you like the functional group. And this is a beta keto ester. The reason it's called that is because alpha, beta, alpha, beta. So compared to this carbonyl, this second carbonyl is beta. Compared to this carbonyl, the second carbonyl is beta. So they are beta to one another. This side is a ketone. This side is an ester. So in general, these guys are called beta keto esters. A specific beta keto ester that we're going to use often in this class, or often, is the acetoacetic ester. So this is called the acetoacetic ester, and I spelled that wrong, nice, because this is an acetone, and this is an acyl ester. So we call this guy the acetoacetic ester. So this is a beta keto ester. It's a specific beta keto ester, but we cannot say that every beta keto ester is an acetoacetic ester. The reason I go over this is because usually Dr. West likes to ask a question where he puts up a picture of something that looks almost like this, but let's say it's like this. And he says, which of the following is a correct name for this? And answer choice A is beta keto ester. Answer choice B is acetoacetic ester. Answer choice C and D are something ridiculous. And when you look at this, this is a beta keto ester, but it is not an acetoacetic ester. Make sense? Ish. I hope. Yes, okay, cool. So, similarly, if we have... Okay, I can explain. Give me one moment, please. Okay, so you know how we have shoes, right? And so a flip-flop is a shoe, but every single shoe is not a flip-flop. So if I have a sneaker or like a high heel, those are both shoes, but those are not flip flops. So beta keto ester is the shoe umbrella, and this is a flip flop. So this guy is a high heel. It's not a flip flop, but it is a shoe. So yes, an acetoacetic ester is a specific beta keto ester. Kind of like saying an ether, an epoxide is a type of ether, but not every single ether is an epoxide. Okay, so on the same like idea, we have something called a malonic ester. So a malonic ester, do you guys see what I'm writing out? Yeah, okay, cool. So a malonic ester is when we have two ester groups on the same carbon, and they are again beta to one another. So very similar to what we just talked about, acetoacetic ester or beta keto ester, except now it's two ester groups that are beta to one another. And so malonic ester is going to be the general name, and whatever we substitute these for will be the more specific name. But he doesn't tend to ask you the name for this one because it tends to be more complicated. This one is an easy one that he'll get you with. So I'll zoom out so you can just see that. Okay, so let's go back up here and let's finally do this reaction. So we're going to look first at each step and we're going to break it up and we're going to turn this into an easy peasy lemon squeezy reaction. So in this first step, we have OUT and we have phenyl CHBr. So these reagents are for what kind of reaction that we learned about? We have a base and we have an alkyl halide. So what reaction do you think we're going to do? Hint, we talked about it today. An alkylation, exactly. So I'm just going to write here, alkylation. All right. And we have NaOH and H2O. So we have water and we have a base. What reaction type could we have here? Think back to chapter 16 and 17. And it could be super general. It doesn't have to be super specific. Yeah, we could do some kind of hydrolysis. So For now, let's just say some kind of nucleophilic substitution, and we'll talk more about it. So we don't know what heat is used for yet, so we're also going to leave this for a second. So we have one carbonyl, and this one has alpha 1, alpha 2. The second carbonyl, we'll also call this alpha 2. It only has one alpha position, right? So we can either replace this side, which is the alpha position for 2 carbonyls, or we can replace this one. Which one do you think is more likely to be replaced? Excuse me. So yeah, alpha 2 is going to be replaced because this spot is super acidic. Oh my gosh. It's super acidic because it's alpha to both of these guys. So in the first step, that's much too dramatic, we're going to replace the middle hydrogen with our alkyl group. And the alkyl group had one carbon and then the phenyl. So we have one carbon and then the phenyl, which I don't want to draw every time, so I'm just going to write out pH. And at this point, we have A. All right, so in this next step, we said that we're doing some kind of nucleophilic substitution, right? And we know that for a nucleophilic substitution, we're going to take the nucleophile. I'm sorry, the palm rejection is so bad. So we're going to label the leaving group. This is the only leaving group in our molecule. We label the nucleophile. And we get rid of a hydrogen. And we end up with bam, 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 bam. Bam, bam. And now instead of an ester, we have created a carboxylic acid. Any questions on how I got to this point so far? Okay, so the heat is going to do something called a decarboxylation. And you haven't seen that before really in any other reaction, so let's talk about it. So in the decarboxylation, the first thing we're going to do is we're going to rotate this so that the OH is facing the carbonyl. So we get this side stays exactly the same. And our group here stays exactly the same. We don't change that. What we do change is now the purple OH is pointing up and our carbonyl is pointing down. And the reason I do this is so now this OH can hydrogen bond with this oxygen. So they're going to hydrogen bond right here. And we're going to have another one of those circular reaction mechanisms. So this guy is going to just steal the hydrogen. These electrons get pushed back here. And that is actually going to go ahead and break this bond and give those electrons here. So we actually end up getting Bam, bam, bam. And I'm going to draw all the new bonds we made in green. So we made this bond to the hydrogen. We also made a double bond here. And the substituents are a alkyl group and a hydrogen, which was already there, so we're just going to do black. And the side product is CO2. So here we created an enol. And so just for funsies, we know that an enol can go back and forth and can turn into this. So this is the ketone. I know this one was kind of long. It was kind of a doozy. Any questions so far? If not, we're going to take a moment and we're going to go to the next page of the handout. And we're going to talk about a decarboxylation for a second. So something that's really important to note is in order to do a decarboxylation, you need 2 carbonyls and at least 1 must be a carboxylic acid. And I forgot to put here the two carbonyls must be beta to one another. And so a decarboxylation reaction is basically what we just talked about. So let's say we have a ketone and we have a carboxylic acid. First step is we rotate this bond and we get OH. The next step is hydrogen bonding. We steal that hydrogen, break this bond, break this bond. We go in a big old circle and we end up with OH and a double bond, as well as our side product, which is CO2. So this sequence is called a decarboxylation, and our reagent is heat, which is shown as a triangle. So if we go down to this question, it's asking which of the following can undergo decarboxylation. So we know that we need 2 carbonyls. All of these answer choices check out. We know that the 2 carbonyls need to be beta to one another. So yes or no? Are these beta to one another? And then someone asked a question. I will answer that in just 1 second. I just want to go through this question first. So yes, these are beta to one another. How about these? No, they are not. They are right next to each other. So they're not beta. How about these ones? Are they beta to one another? No, they are not. They are much too far apart. They are not beta. Last but not least, are these two beta to one another? Yes, they are. Cool. So we're down to A and D. The last thing is at least one of these guys has to be a carboxylic acid. So which one is our answer? D. Awesome. I agree with you. Oh, excuse me. Okay, so going back to the actual reaction mechanism, someone asked about where the hydrogens are coming from. So these two hydrogens, I didn't draw them out until the last step, but they were here. That's where they come from. And this hydrogen was stolen by the other oxygen, and that's where this hydrogen comes from. Does that clear it up? Is there any other question you have on that? I hope I answered your question. If not, let me know. Yeah, it's entirely an intramolecular reaction. And we can say it's like a cleavage because we broke something off of it. Makes sense. Good. I love to hear it. Okay, so we are going to end today with the malonic ester synthesis, which is the last reaction of the chapter, the last reaction we're going to do this semester. Yay! So, as I told you, it's almost exactly the same as the last one we talked about. So we know that this is an alkylation. We know that this is a nucleophilic sub. And now we know that this is a decarboxylation. The only alpha carbon we have is this one. So in the first step, we are going to this is such a big molecule for no reason. I made it up for no reason. So we are going to add to that alpha position the same group we had last time. And remember, we still have a hydrogen here. And at this point, we have A. Now, A is going to react and do a nucleophilic substitution. Last time, we substituted one of the esters. Now, can we pick which side to substitute? Are we going to substitute both, neither, left, or right? What do you guys think? Left, right, both, neither. Which one are we going to substitute? Okay, someone said the right. This was another one of those tricks. You have no way to pick. This is not a specific reaction. It's going to go ahead and substitute everything it can. So we're going to substitute this side, and we're going to substitute this side. So we've turned both of those esters into carboxylic acids. I don't want to confuse anyone, so let's do that same. So at this point, we have B, right? So in order to do a decarboxylation, you need two carbonyls, check. They need to be beta to each other, check. And at least one of them has to be a carboxylic acid, check. So this can happen between two carboxylic acids, that's fine. So in the decarboxylation step, I am going to draw this step out, or this reaction out step by step because we just covered it for the first time. So we rotate that. I'm going to copy and paste because I am truly too lazy to draw that again. And all we're doing is, that's what I get for being lazy, I guess. We're flipping around the carbonyl and the OH. And we know that heat is going to make this guy steal the hydrogen, which is going to break this bond, give those electrons here, which breaks this bond, give those electrons here. It's almost like a reverse Diels-Alder if you think about it. If that confuses you, don't even think about it. So our final answer is very colorful. All right, so this is the base we had already. Nothing changes here. But now we did steal this H, and we did create a double bond. And we know that our side product is CO2. And we know that this can do a tautomerization, and it can become this guy. Again, so much to draw. So much. From now on, I'm not going to do color-coded. It's just simply too much work. I'm kidding. Someone said I definitely have to rewatch this. I totally feel that. It is truly a lot. We covered a lot today. It is kind of confusing at first, but once you get it, and like you've done it a couple times, hopefully it'll start clicking and making sense. And then hopefully it'll be easy peasy. All right, so again, I know that was a lot, but do we have any questions, comments, concerns, anything of the sort? All right, so let's go back to the last page of the handout. And according to Dr. West, Chapter 19 will not be on the exam, so you can go ahead and just cross this whole thing out. We don't need to cover it. So get rid of it. And yeah, that's pretty much it. I'll zoom out so you can see this whole thing. Oh, here you go. This whole thing. And that is honestly all I have for you guys today. I say that as if we're not already 5 minutes over. I apologize. We started a little bit late because I was having technical difficulties. But yeah, we finished. We're officially done with the semester. All we have left is to review. So I'm excited. I hope you guys are excited. Woo. All right. Well, I will leave it there. I'm going to stop talking. If you have any questions, I'll stick around for another minute or so. But if not, have a wonderful day. You're very welcome. Bye.